Hi everyone, welcome to the first lecture of Chem 100, Introduction to Matter. There are going to be plenty of definitions that we're going to cover in this lecture and lectures moving forward. The best thing for you to do is get out your flashcards and start writing definitions out as I go through the lecture. This way it will expedite your time. So matter defined. This is anything that has mass and occupies space. Matter is composed of atoms. So if matter is composed of atoms, we're going to need a definition for what an atom is. It's the smallest particle of an element that can exist and still contain the properties of that original element. Now, it's really important that you don't drop off half of that definition because there are other particles of an element that are very, very small. Subatomic particles, for example, like electrons and protons. But those subatomic particles cannot exist and still contain the properties of the original element. So we don't want to lose any of that definition. Atoms are also too small to be seen with the naked eye. And I'm giving you these values just for reference. It's not something I'm going to test you on. But we're talking about 4 billionths of an inch and electron microscopes that photograph atomic images with magnification factors in the millions. So these little dust particles that you see floating around in the air, atoms are much, much smaller than that. You cannot see atoms with the naked eye. The definitions of mass and weight differ, and you'll need to know how. Mass is the amount of matter in a body, and we usually measure mass in the lab in grams. Weight, on the other hand, is the measure of the Earth's gravitational attraction for a body, and that is usually measured in pounds. Matter can have different physical states. We're going to look at 4 different physical states, starting with the solids. Solids have definition in their shape. They don't have to assume the shape of their container. The particles, that is the atoms or the ions that the solid is composed of, adhere rigidly to one another. They line up like soldiers. There are 2 types of solids, crystalline structures and amorphous. Now the ones that line up like soldiers in a crystal have regular repeating units. They have long range order and their particles are very well ordered. Again, they line up like soldiers. On the other hand, we can have amorphous solids. Examples of amorphous solids are plastics, glass, and gels, and the units are irregular. In other words, they don't line up like soldiers, they don't have long range order, and they don't have a regular repeating unit like a crystalline solid would. Examples of crystalline solids, salts and sugars. Another physical state of matter is a liquid state. Liquids have a definite volume, but the particles can slide past one another. They're not rigidly adhered like they are in a solid. They're very close together, but not rigidly adhered. There's no definite shape. Liquids will assume the shape of their container. And so if you spill a glass of water on the counter, it's going to try to take the shape of the room. So it's going to go across the counter and onto the floor. Clearly, it can't take the shape of the room because the volume is going to be maintained. So the volume won't increase or decrease. Gases, another physical state of matter, have an indefinite shape and volume. A gas will completely fill its container. So if you open a bottle of perfume in a room, pretty soon everyone in the room is going to be able to smell it. They assume the shape and the volume of their containers, and the particles move independently of one another. So the particles are not rigidly adhered. They are not tightly packed. They move independently, and there's a lot of space between them. Plasma is the 4th state of matter that we're going to discuss. It's more recently determined that plasma is a state of matter than liquids, solids, and gases. It used to be, in fact, thought that liquids, solids, and gases were the only 3 states of matter, but now there are more, and plasma is a very important one, so we're going to discuss it. If you had a gas and then you heated it up so that you got it very, very hot to the point that it would ionize, that gas would become plasma. It would contain light and photons and charged particles such as electrons, positive ions, some negative ions. Stars are plasma. For example, the sun, 6,000 degrees Celsius at the surface, and there are fusion reactions that release enormous amounts of energy. Lightning strikes, for example, are plasma. Your plasma television screen, your cell phone has plasma. Your computer is composed of plasma. This is a very, very important current state of matter in our society. So here's a learning check for you to think about the states of matter that we've just discussed and the characteristics that are associated with them, and determine if you can pinpoint what state of matter we're talking about when we describe some characteristics. Some unknown matter has particles that move independent of one another and carry no charge. This matter can be colored or colorless, will fill an entire room. What physical state is this unknown matter? Now, you may jump to a conclusion, but in chemistry, what we like to do is go through the major points that we have and think about every point until we actually derive an answer rather than guess or jump to a conclusion. So if we look at that first bullet, while liquid particles slide past one another, gas particles actually move independent of one another. Plasma particles also are very far apart, but they carry a charge, while gas particles do not carry a charge. Some gases, like bromine, for example, which is colored yellow-orange, while other gases, like oxygen, which is colorless. Plasma and gases both fill their containers, but because we know that this particular species doesn't carry a charge and can be colored or colorless, the answer is the gaseous physical state. This brings us to talk about substances and mixtures, because substances and mixtures are a type of matter. But we need to distinguish between the definitions of substances and mixtures because they have a lot of similarities, but they're very, very different. A substance is a particular type of matter with a fixed composition, and we generally refer to substances as being pure. So they have one phase. A mixture, on the other hand, contains two or more substances and has variable composition. And a mixture may have one phase, but it also may have more than one phase. Could have more than two phases or three. So what is the definition of a phase? That's a homogeneous part of a solution that's separated from other parts by a physical boundary. And what does it mean to be homogeneous? Because there's another definition that we have to talk about. Homogeneous means that when you observe that particular system, you only see one phase. So for example, if you mixed sodium chloride in water and you stir it with some kind of a stirring device, even a spoon if you're at home, and you look at that particular solution through a clear glass, you would only see one phase. That's homogeneous. On the other hand, if you mix water and oil and you stir it with some kind of a stirring device and then you observe it through a clear glass, you would notice that it will separate into two phases. That's heterogeneous because you have a homogeneous part of the system, which is water, that's separated from the other part by a physical boundary, which is the interphase of the oil. Again, the oil in water is heterogeneous. The sodium chloride in water is homogeneous. One phase homogeneous, multiple phases heterogeneous. Substances are composed of either elements or compounds. So if we look at Cu and F, that is copper and fluorine. Those are elements. Elements cannot be broken down into simpler substances by physical or chemical means. And again, that's a definition of elements, and you can't drop off any part of it. You can't say an element cannot be broken down by physical means, or an element cannot be broken down by physical or chemical means. You have to leave the whole definition there. It cannot be broken down into a simpler substance by physical or chemical means. Of course, an element could be broken down into its subatomic particles like electrons and neutrons and protons, but electrons and neutrons and protons are not a substance. They are a subatomic particle. Elements can become chemically combined, and so copper and fluorine can combine to form a compound, copper 2 fluoride. This is an ionic compound, can be broken down into simpler substances by chemical means, but not physical means. So again, compounds can be broken down into simpler substances by chemical means, not physical means. While an element cannot be broken down into a simpler substance, either by physical or chemical means, but they are both pure substances. Water, another pure substance, H2O, is a covalent compound and a molecule. Water can be broken down into simpler substances by chemical means, but not physical means. So it would take chemical means to separate the hydrogens from the oxygens in water. It would take a chemical reaction to separate the copper from the fluoride in copper 2 fluoride. O2, oxygen gas, this is a compound and a molecule. It's covalent. Let's talk a little bit more about O2. So if we look a little bit closer at O2 gas, then what we see is that we have two oxygens together. This is called a diatomic molecule. Di for two and atomic for the atoms. It's a molecule because we have two elemental atoms that have come together in a bonding interaction. But it's elemental by definition. So let's think about why would it be elemental by definition. If we look at oxygen here, we see that if we broke this oxygen down, this diatomic molecule down, by chemical means, we would get oxygen and another oxygen. And so therefore, we don't have a new substance. By breaking it down chemically, we haven't formed a new substance. You'll see the same is true if you look at any of these. H2, N2, Cl2, Br2, I2. If we broke I2 down, what we would have is iodine, and we'd have another atom of iodine. I2 is iodine gas, and so we haven't changed the substance, and therefore, by definition, these diatomic molecules are elemental. They are found this way in nature. You have to memorize these diatomic molecules because when it comes to writing balanced reaction equations, you have to write each of them with the subscript 2 because this is the way they're found in nature. Unlike something like sodium, for example, in A, which isn't found as diatomic in nature. It's just found as sodium. There's a mnemonic, a couple of mnemonics down here at the bottom of the screen. So for example, Honkelbrief, H for hydrogen, O for oxygen, N for nitrogen, Cl for chlorine, Br for bromine, I2 for iodine, and F for fluorine. Or you can memorize the other mnemonic that students have given me before, have no fear of ice cold beer. But either way you look at it, you've got to memorize one of these mnemonics, or you have to memorize all of these diatomics, because anytime you write a balanced reaction equation, that balanced reaction equation is composed of diatomic molecules. They're going to be written with that subscript 2. Substances and mixtures, as I told you, have a lot of similarities, but they also have a lot of differences. And so a mixture contains 2 or more substances, and we just talked about compounds that contain 2 or more substances. So that's a similarity. So where's a difference? Well, a mixture can be broken down into simpler substances by physical means. If you remember, a compound cannot be broken down into simpler substances by physical means. We have to use chemical means to break down a compound into simpler substances. Mixtures also have variable composition. So in other words, if we mix sodium, for example, in water, we could mix 1 gram of sodium in 100 mils of water. We could mix 2 grams of sodium in 500 mils of water. We could mix 0.5 gram of sodium in 50 mils of water. All of those solutions would still be a mixture of sodium and sodium chloride and water. On the other hand, if we just had sodium chloride and water independent of one another, and they weren't mixed, when we look at water, we have 2 hydrogens and we have 1 oxygen. And that's always the case if we had water. If we change the number of hydrogens or we change the number of oxygens, we would no longer have water. We would have some other substance. Similarly, sodium chloride has 1 atom of sodium and 1 atom of chlorine, or you'll later learn that it's 1 ion of sodium and 1 ion of chloride that are together. But the fact is that we're always going to have that fixed composition. Where with a mixture, if we mix sodium chloride and water together, we can have variable composition. We can vary the amount of sodium chloride we add to the amount of water. A homogeneous, again, 1 phase, uniform throughout. And some examples of that are dissolving salt in water or dissolving sugar in water. A heterogeneous mixture, 2 or more phases. Sand in water, for example. Or oil and vinegar. Sand and water don't mix, oil and vinegar don't mix, and so you would have 2 phases in either one of those mixtures. So let's do another learning check and see how your classification skills are. So we're going to look at sand first, and we're asking the question, is sand a pure substance, an element, a compound, a molecule, a heterogeneous mixture, or a homogeneous mixture? We know that sand is not a pure element, it's not a pure compound. It's not a molecule because a molecule is also a compound. So it's either a heterogeneous mixture or a homogeneous mixture. And if you look at sand on the beach, for example, you can see that there are shells and they're not evenly dispersed, or maybe there's a bunch of seaweed on the sand, or maybe there's some larger stones in one area than the other. And so if that's the case, then we don't have 1 phase. So it's heterogeneous. Let's look at ice. Ice is composed of frozen water, H2O. H2O is a molecule and a compound. It's a pure substance. Flour, on the other hand, is not a pure substance. It's not an element. It's not a compound. And it's not a molecule. It's a mixture. And when you bake, bakers who are really good run flour through a sifter. And the reason they run it through a sifter is because it starts out heterogeneous, and they run it through a sifter so they can get it more homogeneous so that it's equally distributed throughout their baked goods. Table salt, NaCl, again, so composed of elements. And not only composed of elements, but we see that we have this fixed composition. 1 sodium, 1 chloride all the time. So that means we have a pure substance, and that pure substance is a compound. Characteristics of substances give them a unique identity, and scientists can actually determine an unknown by looking at some of those characteristics that are associated with substances. And the first thing we want to look at are physical properties, because those are the easiest things to determine. Physical properties can be observed without altering the basic identity or composition of a substance. And so when we have an unknown in the lab, we'll look at the color, we'll analyze the odor, the physical state, is it solid, liquid, or gas? We'll measure the melting point, we'll measure the density, we'll evaluate magnetism. All of these characteristics and more we'll look at, because each substance has its own unique physical characteristics associated with it. We can also look at chemical properties once we've looked at all the physical properties. Sometimes chemical properties will tell us something unique about a substance. The difference between a physical property and a chemical property is that a chemical property describes the ability of a substance to form a new substance. And so we're not saying that we've had a chemical change where we've already formed a new substance, but what we're looking at is the ability of a substance to do that. For example, iron has the ability to form rust when it oxidizes, but gold doesn't form rust. That means that that chemical property is specific to iron, and we can identify iron based on that chemical property. When we look at chemical or physical changes and we want to determine, is this a physical change or is this a chemical change, we ask the question, is this process reversible? Now, this doesn't work in all cases, but in many cases it will. If the process is not reversible, then in a lot of cases that means it's a chemical change. But if the process is reversible, then that means it's a physical change. So for example, if you had water, liquid water at room temperature, and you put it into the freezer, 0 degrees C, that liquid water is going to become a solid. If we take it out of the freezer and we sit it back on the counter at room temperature, it's going to melt back to a liquid. We could also convert that water to a gaseous state by putting it on the stove in a pan of water and turning on the heat, or putting it in a beaker over a Bunsen burner and turning on the heat. If the water starts to boil, you'll see some vapor above the top of the beaker, above the top of the pan. If you put a watch glass over the beaker or a lid over the pan, you'll see condensation on the underside of the lid or the underside of the watch glass, and that's where the vapor, the gaseous water, is recondensing into its liquid state. With the water, doesn't matter if it's a liquid, a solid, or a gas, it's still H2O. There hasn't been any chemical change in the composition. Physical change, you'll see the appearance of the substance change, but not necessarily the chemical composition. I just gave you an example of water freezing, melting, and evaporating so that you can get ice, water, and steam. Again, no change in the chemical composition. In all cases, we still have H2O. You haven't separated the hydrogen from the oxygen by freezing the water or heating the water. With a chemical change, the substance undergoes a chemical change and forms a new substance. That's different than a chemical property, remember, because a chemical property means that a substance has the ability to undergo that change. With a chemical change, the substance has actually undergone that change. So you have a bucket of nails, iron nails, that you leave outside in the rain, and they form rust. That's a chemical change. You can see the rust on the nails. It's going to take some kind of a chemical reaction to get that rust off of the nails. It's not going to just go back to unrusted nails if you take it out of the rain, for example. A compound is a distinct type of substance, chemically combined in definite proportion or fixed composition. Now, I know it drives students nuts when we start using different terminology and they see it on a test. So I generally, rather than throw you a curveball on a test, like to cover different terms that can be used during lecture so that you're aware. So definite proportion or fixed composition by mass, those have the same meaning. And here's an example. So if we had water, there's 2 hydrogens and 1 oxygen in water. That's a fixed composition by mass, or a definite proportion by mass, because all hydrogens have the same mass. You'll see that it's an average as we start to talk more and more about elements and compounds in the periodic table. And all oxygens have the same mass. And again, you'll see that that's an average of isotopes when we start to talk about that. If, for example, we had H2O2, we would not have water anymore. We've changed the composition. And so now we have a completely different substance. We have hydrogen peroxide. Compounds are pure substances that can be decomposed into simpler pure substances, again, by chemical but not physical means. So iron 2 sulfide, for example, can be broken down into iron and sulfur by chemical means. There are two different types of compounds we're going to discuss in this class: molecules, which are also called covalent compounds. H2O is a molecule, H2O2 is a molecule, and we're going to talk about ionic compounds. Ionic compounds are composed of species that transfer electrons. Molecules and covalent compounds are composed of species that share electrons. So when you're talking about molecules or covalent compounds, sharing of electrons is what you need to keep in mind. Ionic compounds, transfer of electrons is what you need to keep in mind. So let's have a learning check and determine whether or not you have the skills to predict whether a change is chemical or physical property based. Magnesium metal is gray. Is that a chemical or physical property? Well, all magnesium metal is gray. That's unique to magnesium metal. The only way we could change that color is if we ran a chemical reaction and maybe burned that magnesium and turned it into ash. So that has to be a physical characteristic or a physical property of magnesium. Magnesium metal tarnishes in the air. If magnesium metal has tarnished in the air, that means a new substance has formed on that magnesium metal that we can see, some black substance that we call a tarnish. It's an oxidation substance. That's a chemical change. Magnesium metal melts at 922 K. Well, if you think about it, once the magnesium metal has melted at that high temperature, if we put that magnesium metal back to room temperature, it's still going to be magnesium, but it's going to solidify. So there hasn't been any change in chemical composition, only a change in the physical state. So that's a physical property. Magnesium reacts violently with hydrochloric acid, and indeed, when that reaction occurs, you're going to release H2 gases. And so magnesium reacting violently with hydrochloric acid is a chemical change or a chemical property. A molecule, as I told you, is a covalent compound. This is a group of two or more atoms that function as a unit because the atoms are very tightly bonded together. We can have homoatomic molecules or heteroatomic molecules. Homoatomic molecules, all the atoms present in the molecule are of the same kind. For example, ozone, O3. That's a homoatomic molecule. A heteroatomic molecule has two or more kinds of atoms that are present in the molecule, and we've been talking a lot about H2O, water, which has oxygen and hydrogen. Diatomic molecules, again, here's that Hunkelbrief that you have to memorize. That's a molecule that contains two of the same types of atoms. This is the simplest type of molecule. Ions are an atom or a group of atoms that is electrically charged because it has lost or gained electrons. Now, atoms have protons, which are positively charged, and electrons, which are negatively charged. But the protons, unless you're discussing nuclear chemistry, which we don't discuss in this class, remain in the nucleus. What we lose or gain is the negative charges, the electrons, and we designate protons with a positive charge. So here we're talking about protons down here. We designate them with a +1. And we designate electrons with a negative charge, and we just use -1 for that designation. If an atom has lost one or more electrons, then it has a greater number of protons compared to electrons because atoms start out with equal numbers of electrons and protons and they're neutral. So if we look at lithium, for example, lithium has 3 protons, and in its electron cloud, it has 3 electrons. Now, let's suppose that lithium loses one of those electrons. Let's just take that one away. You can see now that there are 3 protons, so we have 3 positive charges, and there are 2 negative charges. So 3 minus 2 leaves us with a +1 overall charge on that ion. That's called a cation. It's an atom that has lost electrons and become positively charged. An anion is an atom that has gained electrons, and so it has become negatively charged. And if we look at oxygen, for example, oxygen has 8 protons in the nucleus. And oxygen also has 8 electrons in the electron cloud. When you have a -2 charge associated with it, will gain 2 electrons. So you have 8 protons and 8 electrons, and if we gain 2 more electrons, then we have a total of 10 electrons minus 8 protons, which gives us a total charge of -2. 2 more electrons, 2 more -1 charges relative to the number of +1 charges that we have. Elements are the fundamental or elementary substance of an atom that cannot be broken down into a simpler substance by either chemical or physical means. Now remember, again, we said that an element can be broken down into simpler subatomic particles, but subatomic particles, again, are not substances. So cannot be broken down into a simpler substance by chemical or physical means. Elements are pure substances and they have a fixed composition by mass. For example, copper atoms all have the same average weight. Silver atoms all have the same average weight. Gold, iron, any element you want to look at has the same average mass associated with it. So we have a fixed composition by mass again. The periodic table is an alphabet of elements, and I'm just going to say right now, because students always ask me this as soon as they see periodic table come up on a lecture slide. No, you don't have to memorize the periodic table. I do not ask students to memorize the periodic table. There are very few scientists who have ever memorized the periodic table, although there are some, but we always have a periodic table in the lab that we reference. Elements are written on the periodic table, some of them with an uppercase and then a lowercase, like sodium, uppercase N, lowercase a. That's the chemical symbol for sodium. The chemical symbol for calcium, uppercase C, lowercase a. Chemical symbol for iron, uppercase F, lowercase e. You cannot write your own script. You need to follow the same script that is historically written in terms of chemical symbols or chemical formulas. And so a lot of you probably have fancy handwriting, but you're going to have to bring it down to the convention that's always been used with chemistry in terms of writing formulas. We want other people to be able to read what they're looking at, and so there's a specific convention. Some elements are written with uppercase only, that is hydrogen with an H, oxygen with an uppercase O, and carbon with an uppercase C, and there are many others, nitrogen with an uppercase N, phosphorus with an uppercase P. And so you'll just have to look at the periodic table, and you'll always have a periodic table on exams, so you'll be able to use those periodic tables on exams. I try to give also periodic tables that have names. I don't expect you to memorize names and symbols. What'll happen is, in the case of working with the periodic table, you'll automatically start to memorize these things. So it won't be a side effort that you have to make. In terms of classifying elements, there are physical properties associated with these classifications, and the most simple way that the periodic table classifies elements is by metals and nonmetals. So with metals, I like to have students just think of aluminum foil because that's something that you know. All of you have seen aluminum foil. Probably most of you have used aluminum foil. And so if you can picture aluminum foil, this is your key to understanding the characteristics of metals. And then non-metals are just exactly the opposite characteristics of metals. Aluminum foil is solid at room temperature, and all metals are solid at room temperature except for mercury. Aluminum foil is shiny. That means it has a high luster. It's a good conductor of heat and electricity, and so think about this. When you're cooking something on the grill and you don't want it to fall through the grid, you can put aluminum foil there and it conducts the heat into the food, but it has a very high melting point, so it doesn't melt on the grill. Conducts electricity, so if you rolled the aluminum foil up into a very tight sort of wiry twine and stuck it into an electrical outlet, don't try that at home, but you would definitely get a jolt, a pretty nasty jolt. So again, don't try that at home. Of course, it's malleable, that's why it's rolled into a sheet. And it's ductile, that's why you could twist it into a wire if you wanted to. And again, high melting points and high boiling points. High melting points because it doesn't melt on the grill. You can even use it to line pans and put it in the oven at fairly high temperatures. Non-metals are going to be exactly the opposite of the aluminum foil that you already have in your memory. They're non-lustrous, they're not shiny. So substances like sulfur or carbon or nitrogen, not shiny. They're poor conductors of heat and electricity. They're brittle, they're not malleable, and so if you start pounding them, they're going to crush and break. And they typically have very low melting and boiling points. Here's a periodic table that's showing you metals and non-metals, and so you can see that the periodic table is mostly composed of metals. They're all in the yellow region. The non-metals are blue over there on the right side. This periodic table also has this red stair step, and if you look on either side of that red stair step, you see these green blocks, and those green blocks are metalloids. They have characteristics that are somewhere between a metal and a non-metal, but each and every one of them is slightly varied, and so we can't look at them as a group. We would have to look at them independently as to how much they vary between a metal and a non-metal. Notice that aluminum and polonium are the two that are on that red stair step, but they are metals, and so they have the characteristics of metals, and we just talked about aluminum foil, so you know aluminum. Over here we have noble gases, and noble gases are special because they're what you call inert, I-N-E-R-T. Inert means that they're basically non-reactive. And so we don't see noble gases getting involved in a lot of reactions that we're going to be looking at. They're very, very stable. That's why they're non-reactive. There are a couple of other things that I want to point out to you, and one is the representative elements. The representative elements are all those that you see this A associated with. So this on the left, and then these 6 columns over on the right. Those are representative elements. In the mid section here, these are all B. You can see the B's associated with those. Those are all transition elements. And the lanthanides and actinides are also transition elements. They're inner transition elements. They insert the lanthanides between atomic number 57 and 72, and the actinides between atomic number 89 and 104. We pull them out and set them down below the periodic table just so that we can see it on one page easier. Those are the only parts of the periodic table that I want to point out to you getting started and moving forward. We're going to start into the periodic table rather slow. There's a lot of information that you're going to learn associated with the periodic table, and so we don't want to learn it all at once. This is just a list of what I just pointed out to you, and that is the end of this particular lecture.